Hello, everyone. Can't see you all because of the light, but anyway, welcome. So what am I going to talk about? I'm going to talk about, let me read this, a new way to understand the quantum world. Now, this can mean a lot of different things. So new way can mean, well, somebody is just some weird crackpotty ideas and says they're going to explain everything in some completely different way, which makes no sense. So that's not what we're going to do, obviously. Otherwise, I wouldn't be sitting here. I would be sort of... what do you call that? Like this thing they put you in a mental hospital. So what do we mean by new way? In first order, new way for us means new language. We're going to talk about quantum in an entirely different language than it's usually talked about. The usual language of quantum is something you need to have like a proper university degree for, and you probably learn about it like the later years of your university education, and then the real quantum applications would typically be postgraduate level. So that's a sort of prerequisite of the usual language of quantum. So we're going to take this down. But taking it down doesn't mean that it's less mathematical. I should stress that. In some way, you could say this is maths-free quantum mechanics if you have a particular preconception of what maths means. But what I'm going to show you tonight is as much maths as any maths. In fact, it comes from the most abstract maths that ever been developed in human mathematical blah, blah, blah. It's maths which was developed like in the last 60, 70 years. But, as you will see, it takes a very intuitive and simple form. It's particularly applicable to quantum, so you can actually learn quantum in a very simple manner. So that's what I mean by new way. On the other hand, the new way comes also with a new view on the world. And I'll comment about that as we go. To some extent, we have to go back 2,500 years to change our mindset. We have to forget about 2,500 years of Western scientific progress. Are you ready for that? Good. Okay, something about myself. So I was for a long time a professor at Oxford University from 2001 till 2020, something-ish. There's some colleagues of me, like Alex Kissinger sitting there, kind of took over all the trash I left behind there. And he has to deal with everything now. Some other colleagues here of me. Then I moved to Quantinuum, which is now kind of the leading quantum computing company in the world. Some Quantinuum people in the audience too here. I also got a distinguished visiting, I can't remember how it's called, distinguished visiting chair at the Perimeter Institute, which is a research institute in Canada, which I think many of you must know about because they have a lot of outreach activities and things like that. So anyway, that's where I am. Okay, let's start. Move. The language of quantum. So I was going to talk about language of quantum. During this talk, I'm going to ask questions. And then you have to shout. It's very hard for me to see who shouts first because of the lights in my face. So I expect you to be honest. And if you shout first and you're right, you win a prize. Okay? So who's going to assist me? Somebody going to assist me, like handing out the books?
Hello.
Oh, that's you. Okay, perfect. So, but you have to look who shouts because I can't really see much because of the lights. Okay, we're going to start with our first quiz. All ready?
Yes.
Who is this?
Me.
No. Yeah, so there, up there. I hear it somewhere there. Who was this?
Who's over here?
Okay. I can show it, it's there. So that's what was...
John von Neumann.
It's okay, you win. First prize. So this is... Yes?
Back down.
Yes? Applause for the winner.
And I'll take that up. I should have taken it when I went up first.
So this is John von Neumann. So John von Neumann is known for a lot of things, like he's the originator of game theory, so what's now the foundation of economy and all of that stuff. He's the originator of the architecture of every computer you have. So the sort of classical architecture of a computer is also due to von Neumann. There's a lot of other stuff due to von Neumann in the foundations of mathematics and lots of things. But John von Neumann is also the father of the current language of quantum mechanics, which everybody uses. That's another thing he did. But okay, so I mean, he was probably one of the most brilliant mathematicians of the past century, if not the. If you think about all the technological stuff which he did too. But what for me makes him particularly unique is the following, which many scientists simply can't do. So von Neumann published his book, The Mathematische Grundlagen der Quantenmechanik, which is the mathematical foundations of quantum mechanics, in 1932. And in 1935, 3 years later, after this book, he wrote to his mate, Gerrit Birkhoff, an American mathematician, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. Hilbert space was his brainchild, which he used as the language of quantum mechanics. 3 years after he published his book about it, he denounced his own formalism. He said, this is not the right thing for quantum mechanics. I just used it because it was available, but it doesn't feel right. This is something which doesn't happen very much in science, that somebody so openly denounces their own thing. Everybody's still using it, by the way. Well, not everybody. Like there's some people, we are changing it now, but until recently, everybody was just using that and nothing else. Right, so let's dive a little bit in quantum concepts. So one of the things von Neumann is particularly responsible for in the quantum mechanical formalism is the idea that if you observe a quantum system, so you're going to look at a particle, you want to figure out where it is or something like that, then in the process of doing so, you disturb it. And that's called von Neumann's collapse postulate. The particle goes in a certain form which is particularly comparable with the kind of question you ask. Because quantum mechanics is all about asking questions. Then when you ask a question, you get an answer. As probably most of you know, the answer you get will be non-deterministic. It can be probabilistic. Different answers can come out for the same state. But what is even more important is after you get the answer, the system goes in a state that reflects the answer. So suppose, like, just to give one example, so you don't know who you're going to vote for, you're sort of undecided. The moment you vote, you're actually convinced that what you voted for is what you wanted to vote for, which is right. So your mind shifts. We got a specialist on these sort of things. Where's Emmanuel? Emmanuel, is he not here? He works on that sort of stuff. Are you not here? Okay. Where are you? Where is he? Oh, there he is. He works on this kind of stuff, psychology, like modeled by quantum stuff. Modeled by quantum stuff, like this sort of decision-making and stuff like that, modeled by quantum. I've got another metaphor here. Like, suppose you got a child, and it wants to know where the balloon is in a dark room. So the child's going to walk in the room, the balloon is there, it's going to look for the balloon, but obviously, the moment it finds the balloon is going to move away because the child touches it, you know? And the balloon is way too light, so the moment you touch it, it moves away. It's kind of the same idea, like this pictorial effect. So that's von Neumann projection postulate, which is a very important aspect of quantum mechanics, that if you observe something, the thing will change, and it will reflect the answer you get to your question. And for von Neumann, this was the most important aspect of quantum mechanics, and because von Neumann was so smart, everybody followed him in that belief. The most important aspect of quantum mechanics is the fact that when you observe something, it changes. Does that make sense? If something doesn't make sense, tell me. Okay? Yeah? Okay, it makes sense. Okay, good. So that was von Neumann's idea. I think we got another quiz coming. Who's that? Oh, that was difficult. So who was that? I don't know, lots of people.
I heard first over there, but I'm not going upstairs.
Okay, yeah, so Erwin Schrödinger. So, I mean, you probably all know Schrödinger. Oh, am I moving? Yeah, from a cat. And he also was responsible for an equation which tells you, like, how quantum mechanical particles are actually like waves. So you see the picture of the dead and alive cat and quantum mechanical particles being wave. For me, that's not the most important thing von Neumann Schrödinger came up with. For me, this thing embodies a much more important observation which nobody took notice of at the time and which only like in the last 20, 25 years people start to appreciate. So what Schrödinger said was that when two systems enter into temporary physical interaction, this really means nothing else that there are two systems. They're here, one, two systems. Then stuff happens. Stuff happens that has no counterpart in our classical world physically, in our classical physics world and the way, because new states start to emerge. Things which are not like, okay, the description of these two particles is the description of one together with the description of the other. No. Things emerge which are more like a relation between these two things, rather than these two things having an identity in their own right. They may even completely lose their identity and just become a relationship. I'll give a metaphor later. But so that's what Schrödinger identified as the most important aspect of quantum mechanics. So for like 70 or more years, everybody was following von Neumann's idea that if you're going to understand quantum mechanics, we need to focus on what happens in a measurement process. Very few people focused on the idea that the most important thing about quantum mechanics is what happens if you bring two things together. So I got another slide. Okay, just to give you a little bit of a metaphor here, to give some idea of what we're talking about. Consider the concept of twins. I just say twins here. So what do you know about twins? Well, nothing. If I say, okay, this is somebody who has a twin, what do you know about the person? Nothing. The only thing you know is that if you learn something about that person, then the other twin will obey the same property. Their hair color will be the same, their skin color will be the same, their eye color will be the same, things like that. But you know nothing about them. That's kind of the idea of an entangled state, a maximally entangled state of quantum mechanics. The individual have no properties, but what you know is that whatever this one is, the other one is too. I'm talking very sort of metaphorically here. I'm not giving you an exact presentation, but just to say that this is very different from describing a thing by saying what is this thing and what is that thing. It's really a relationship between the two. In Western scientific development and stuff like that, since Democritus, people have tried to understand things in the way they are made up. So if you want to understand physics, then you want to know what are the smallest particles. And maybe the smaller particles are made up of even smaller particles and things like that. That's how we try to understand everything. That's why the dominant branch in physics is particle physics, has been particle physics for a long time, because that's how people want to understand things. In mathematics, it's similar. People want to understand mathematics and mathematical structures by how they are made up. So you go down to the elements. You want to know what are the elements, and so the smallest particles. In biology, you want to know the genetic code. What is sort of the code which underpins everything? So it's reductionism. It's atomism, whatever word you want to throw at it. And this all goes back to Democritus. Leibniz had a different idea. Leibniz said, we understand a thing in its relation to other things. He particularly posed this about space-time. This was his view about space-time. But of course, you can think about this for anything else. Like, if you meet a person somewhere, are you interested in how this person is made up? Are you going to take your butcher knife and then start chopping and see what's inside? That's not what you usually do. You won't establish a very good relationship with that person in that way. So what you want to do, and I said it just, you want to establish a relationship with that person. So what you're doing is you build a relationship. And that's the connection to that person. That's your connection. And I think we as humans, we naturally think in terms of relationship. Children think in terms of relationship. We grew up thinking in terms of relationship. But then when we are taught science, we unlearn this. We more and more start to think about how a thing is made up, because that's how our scientific programs are mostly set up. In the exact sciences, in the positive sciences. So in that sense, Schrödinger took us back quite a while by saying, no, we now need to think about two systems and how they are related in quantum mechanics, and it's the best way to understand things. So it really takes us back a while. Enough said about Schrödinger. I think we got another quiz coming. This is going to be even easier, I think. So how should we do that? We should do some constraint here. I don't know. Come on, not you. You already got one. Okay, well, let me ask something else. Like, what did he get the Nobel Prize for? Okay, we got somebody there. Okay, so that's Roger Penrose, and he got the Nobel Prize for black holes, which you see on the right-hand side. In case you didn't know, like Roger Penrose was a very good friend of Escher. His father actually was initially a good friend of Escher, so Penrose contributed to a lot of the Escher paintings. Like this is really Penrose's staircase, which became an Escher painting. So they were closely connected. Something else that Penrose did, again, much less known, is the following. So Penrose, when he was an undergraduate student, he needed to study general relativity, and the things on the left in the squiggly arrows are sort of symbolic representations which you encounter in general relativity. The thing on the right-hand side is stuff he denoted in his notebook, because he didn't like the stuff on the left. And you can kind of see how it goes. You see, you got this Q there, and this Q becomes the blob. And then you see you got these subscripts FG, they become like wires with two inputs. Then you got these superscripts ABC, they become wires, but on the other side. So in a way you have to think of the F and G as some sort of inputs, and the A and the B and the C as some sort of output. So he took like this symbolic representation and he changed them for diagrammatic representations. That's what Penrose did. We're talking probably late 50s here. He never published this in a paper until somewhere in 71 in an appendix. So this thing was considered as marginal. That's why people would say math-free. And when I was talking about math-free, it's really this translation of Penrose from the symbolic representation to the diagrams. It's not math-free. It's a different kind of math. So we got three ingredients here now. So von Neumann wanted the new quantum formalism because he didn't like his own. Schrödinger said quantum is about composing stuff, like what happens and relationships you build between things if you bring things together. Penrose uses pictures instead of symbols because he thinks it's nicer and more intuitive to reason with. So these two turn out to be one and the same thing. Looking at the world on how you compose things together, more than anything, like as your first view on the world, like it's all about what happens when things come together, the relationship which get established. And drawing things as pictures turns out to be exactly one and the same thing. That's a very important observation, which was initially made by within the field of computer science. People thinking very abstract about computer science in the late 90s, early 2000s, they start to basically realize that composing programs, composing data types, all of that stuff was basically similar to like drawing flowcharts, if you want. Because it's quite similar to flowcharts, what I'm talking about. And I remember when I got my first programming course, which I can't remember, it must have been in the 80s or something like that. Yeah, we had to learn flowcharts as the first thing. And effectively, later we realized that these flowcharts were like actually hardcore mathematics in some way. And you'll see what I'm going to talk about. So here's, hey, my font has changed. Don't like that. Doesn't matter. Quantum in pictures. So that's what you can win. That's this book. It's a book which Stefano and I brought out in early 2023. Before that, there was a book. I mean, I should have brought a copy of it, but I forgot because it's too heavy. Nobody has the Dodo book here? No, I don't think so. It's a book I wrote with that guy there a bit earlier in 2017, which was really thick, and which is a course we taught at that time at Oxford University together, starting in 2013 or something like that. So these were the course notes, but this was like a postgraduate course, fourth-year postgraduate course. So we did present quantum mechanics entirely in a sort of language like Penrose's, like entirely in terms of pictures, this new mathematical language. I started working on that in 2003, so it took us some 15 years to get there and get it all right. But so, yeah, we started teaching at Oxford University. Now, this course is not something just anybody could pick up, like a 15-year-old, 16-year-old couldn't just pick that up and start learning. It would be too hard. You need to know some matrices, you need to know some linear algebra. We actually construct von Neumann's formalism from the diagrams and all that, but that's not the subject of today. So what did we do with this book? This book had another goal. Hello there, I want to learn some quantum. Maybe you think you don't know enough math. Well, that's not a problem. The pictures in this book are a new kind of math that will teach you all about the quantum world. Yeah? So that's what's in the new book. No questions, nothing, no comments. Okay, and so then in around Christmas, there was this article in the... Oh, yeah, yes.
Hold up.
You have to wait.
Thank you. Yeah, you know the book you talked about, the other one that you wrote in, like, I think you said, like, 2017?
Something, we wrote it over 3-4 years, but yeah.
Something like...
It was the most horrible part of my life. But okay, every day waking up. Yeah. It was 1,000 pages, so...
Yeah,
and 5,000 pictures, 5,000 pictures.
is it still published? Like, is it still for sale? Like, can we buy it?
Of course.
Yeah, what is it called?
Picturing quantum processes.
Picturing... Isn't that... Okay, no, I don't... You
There's
know
a
the new
Dodo.
book?
It's called the Dodo book, sort of, informally. Huh? Cambridge University Press.
Cambridge University Press, and then the book is called
Picturing quantum processes.
Okay, thank you.
Yeah, it's still completely for sale. Sells very well. So every time we sell one, each of us gets like a beer, like a duvel. That's the royalties. I'm from Duveltown, by the way, in case you know that beer. That's my hometown. Anyway, so there was this article in The Guardian in 2000. Is Zia here by any chance? Can't see it. No, the journalist. Okay, she maybe was going to come, but she wasn't sure. Anyway, so this was a one-page article in The Guardian, and this wasn't just because we had written a book. It's because we had done something with this book. The whole reason to write this book in the first place, Stefano and I, was to do something special with it. And that's what we did. And so here it is, our experiment. So we did an experiment. Lots of people here in the room were involved in that. We had this book. The book was written as the textbook of something, the textbook of a course. So we were planning to set up a course around this. So this was the textbook. Then we took the entire content of that book. We turned into lectures. So we basically, just like you got lectures at a university, you know, we went through the whole book. Different people, several people here in the audience gave some of the lectures of this book. Okay, this could be a good quiz, but this is a little bit more difficult. So what am I explaining? I can't hear it. It has something to do with it, but it's not that. It's quantum, it's not gravity. It's not picturing gravity processes, it's picturing quantum processes. Quantum in pictures, not gravity in pictures. Actually, to be honest, in the book is gravity in pictures too here, but that's not it. What? Okay, but you got it already. No? Oh, no. Okay, good. I'll repeat, quantum teleportation. I'm explaining quantum teleportation there. I'm not going to explain this today, so that's all you get today about that. But quantum teleportation does have something to do with distances and relativity, a little bit like that. So it comes in, and you see this guy there saying light speed, so it comes in. Okay, and then we produced a bunch of sort of exercises. So these were things we could send to people and say, try to solve this. And then I sort of produced solutions to the exercises so they could see whether they did it right. We had a flyer. I mean, it's a little bit small for me to read it. So basically what we did, I don't know if I can read this from here. 3 courses taught by researchers from University of Oxford and Continuum. 3 courses. So we told people, okay, there's a free course you can take. You don't have to pay for it. And upon completing the course, you will receive a certificate, unconditionally, which was important, unconditionally. So however good, however bad you did, didn't matter. You get a certificate, you can apply to a good university with your certificate of a quantum course. Yeah, that was the idea. That was the idea. And so what we got about 1,000 applications. It had to be in the UK for lots and lots of... Just to be able to do this and send this out, it took Oxford University a year to give us approval. Right? And this was just for the UK, by the way. So we got 1,000 applications from the UK. we pretty randomly selected about 70 students out of it. And so over a period of 8 weeks, we gave them the course so they had a textbook, they had to watch a lecture every week, and then they had a 1-hour tutorial session with a tutor where they could ask questions. And then we gave them some homeworks, which they could try to solve. I mean, we weren't checking on it because that was just logistically impossible. It was all online, by the way. It was all online. It was all online. It was really difficult. So, I mean, let me go to the next slide. So basically, okay, no, I'm not going to say that. So basically, we were teaching them a quantum course, over a period of 8 weeks, which is exactly the model of a typical Oxford University postgraduate course. An Oxford University postgraduate course is 8 weeks. You get a lecture each week. You got an exercise session with a tutor, and this goes on for 8 weeks. We did exactly the same thing, but it was online, which is not ideal. And there is something about this particular generation. This was a generation which grew up with mobile phones. Then they had COVID and all of that. So we're talking about students from 15 to 17, 18 years. Here, so high school students. That's what I should have said that. High school students. So whenever we were trying to talk to them, we had just black screens. Whenever they asked a question, they typed it. So there was zero teacher-student interaction, which you usually have, like that you can look at somebody's eyes, that you can listen to somebody's voice to get some idea of how they actually perceive what you're saying. This is a very important part of teaching. Just looking at people's faces, you know. It's very important. We saw nothing. Or listening to the voices, we hear nothing. And then I wrote a very angry email, not angry, like, but come on, show your face, we can't teach like that. And then one person showed the camera for 3 seconds and then it went off again. Is there anybody here in the room who was in this experiment, by any chance? No? Nobody? No, okay. Because I gave some lectures at the Goethe Institute and then some of the students actually showed up. I mean, we hadn't seen them, we didn't know they were, but yeah, they showed up. Anyway, so they took the course, and so the only thing we told them is like, you take the course, and then you get a certificate, whatsoever. At the end, we did ask them to solve some questions. Yeah, for some reason, my fonts have changed, but it doesn't matter. It doesn't matter. It's all readable, I think. So, okay, what they didn't know is that we were giving them an Oxford University postgraduate exam. They didn't know that. So here are some questions. Try to solve them. But these were effectively only questions which had appeared in Oxford University postgraduate exams, translated to the new language, which I'll teach you soon. Translated to our new language. Oh, by the way, the lady who was asking for the book, this is from the cover of the book, The Dodo. So that's the cover of the book we are talking about, 2017. So that's why it's called the Dodo book. Anyway, so we gave them this postgraduate exam. Yeah, okay, whatever. So I said, this was all on one line. This was all on one line, but unfortunately the fun didn't come through here. So 50% of the kids got distinction, which is more than your typical cohort of Oxford University postgraduate students. So they actually did better because of the change of language. Yes. So it's not just for me, there's a lot of people sitting here who are all involved in this experiment, like lots of people, 1, 2, I'm trying to see. Lots of people were involved in that experiment. So I've got a slide somewhere. But yeah, so, I mean, we were hoping that some would do well. But this was just like beyond expectation, especially given what I was saying, the very bad teaching circumstances with the black screens and all of that. We had no clue. In the middle, at some point, I said, okay, let's just call this a day. Let's not do the experiment. Let's just finish the course and that's it. Then I was convinced, like, well, let's just go on with it. We can just keep it quiet if it's going to be as bad as you expect. And this was the result. Okay, anyway. I could ask a question about the bottom right, but it wouldn't really serve this stuff. No association there. Okay, so here are some graphics. I mean, it's a little bit hard for me to see this. So I think the first on the left tells you something about what people knew. So we asked the people, how much do you know of quantum already? And the majority knew pretty much nothing, which you can expect from high school students. Is this visible for you, for all of you? Because I can't read it, but you can read it, so that's good. So if you go under that one, you see hours spent to study per week. I said there were 8 weeks. I see the majority did 1 to 2 hours a week. Nothing more, which is much less than your typical university student would do for a course like that. The bottom right, so this was just a comparison from which schools did the student come from, and you see there is no significant difference between private schools and public schools. There was no significant difference there. So pretty much the same. It's all around 60. Bottom top is actually the most exciting bit, I would say. So we had some sort of open questions. And, well, we had another open question, which I didn't put here. But so like the course strengthened my motivation and confidence. And you see a big majority said yes, which is important. This is very important. Because a lot of people are just scared from symbolic mathematical stuff and all of that. So this is very important. And on the right, the course motivated me to pursue a STEM career. Again, a big majority said yes. STEM means a science career. Science career. So. And then there was some sort of open question. So what did you think in particular about the course? You would expect maybe to say this is interesting, like quantum is a cool thing. No, a lot of the answer was just, oh, this was fun. Very important. It was fun, right? Okay. Right, and then now, I mean, since a year ago, when the Guardian article appeared, lots of stuff has been happening. Like in lots of places in the world, they're now starting to use this. Greece has been the pioneer there. They meanwhile have ministerial approval to start teaching quantum in high school with a big portion of this. So they have the book ready and all of that. I'm talking, this is all in 6-7 months that all of this happened. And so we're at the moment teaching in Ghana. We're teaching this course in Ghana. I mean, there's some other examples which you see. There's actually more than this going on at the moment. That's all that fitted on the slide. So it's more than we can handle, to be honest, like the way it is now being perceived around the world. Okay, so these are some pictures. So a lot of these are, because this was not an easy thing to do, so quite a few people are in the audience. Selma's in the audience, Katrina's in the audience, Hamza couldn't come, Leah is there, Thomas is, I don't know where Thomas is sitting. Thomas is somewhere here, oh, far away. Well, Alex is sitting there, Manuel is sitting there, Pete is sitting somewhere, can't see him. Is Ferdy here? Is Ferdy not here? Come on. Okay, right, your turn. So we're gonna go through this. I mean, it's what is it, like 100? So we don't have that much time. We're going to do this in half an hour or less. So it's some 200 pages. But we are going to go to the end. We are going to go to the end. We're going to skip a lot of stuff. We are going to go to the end. So I mean, this is a lecture theater. So interrupt me. Be sort of bold if something is not clear entirely. We're going to start with wires and boxes. So the language, I mean, I already make reference to flowcharts and stuff like that. So the language we're using is wires and boxes. So the idea is that if you got a quantum system or whatever, it's something that lives in a wire, like electricity, like whatever, like it's particles that flow in a wire. So wires is one part of the formalism. The other part of the formalism are boxes. So boxes are things that do stuff to whatever flows in the wires. I'm going to give you some examples later. Important is you got inputs and outputs. The inputs are at the bottom, the outputs are at the top. Now, let's give some examples. Well, no, okay. Yeah, let me give some examples first. Here, like there. So this is like electricity. So you got a battery, and then you got a wire, and your electricity goes to your lamp, right? Just to give an idea. So that's what we think about the wires. Okay, here it can be water. So you got a pump, and then the water flows through the pump, and then you water the plants. So it's the same idea. Now, what you can do with these boxes is you can plug them together. And that's the fundamental operation. Like if you do calculus and you got two numbers, 2 and 3, you can add them up. You can say 2 plus 3. And you can add them up. Or you can do minus, or you can do stuff. So you get two numbers, you can add them, you can multiply them, you can do stuff with this. Here with these boxes, all you can do is plug them together. See, I got a bunch of boxes, I'll plug them together. But this is conceptually takes us quite a bit away from your usual mathematics. Just for example, you see I've got two wires there, and what these two wires side by side mean is we got two things. We got a thing in one wire and a thing in the other wire. This goes back to Schrödinger, that the idea of bringing things together at a very early stage in the development of your language is the fundamental thing. And this picture shows that even doing something simple here, we're already talking about composite systems, because these two wires side by side means there's two things. There's two things, which things are going to happen to. So it's and in most mathematical formalisms, until 50, 60 years ago, you were always talking about one thing, one monolithic thing, and the way it was made up. That's how so you got a space, vectors, for people who know mathematics, you got a vector space, or you got a group, or you got whatever. It's always one thing. So here we start at a very early stage, the consideration of multiple things together. That's the first thing you do. So these are our wires and boxes. Now, okay, so you've got wires and boxes. Now this thing can apply to everything. This can be a cooking recipe, you know? Like you first take your potato, then you take your carrot, then you chop your carrot and your potato, then you mash them up, then you cook them, something like that. I mean, you can represent it like that. I mean, like a flow chart. So it's very general. So what do we fill our quantum boxes with? Well, let me first give a classical example. So this is an example of such a network, boxes together with wires. You see, this is your computer setup, maybe with your computer, with your laptop, with your tablet. And sometimes wires will be in parallel, because your computer can send to multiple things together, right? So you will have different things coming out. Okay, so that's a simple example. Now let's go to the quantum stuff. So what do we fill our quantum boxes with? We fill them with spiders, right? I mean, that was very much to be expected. See, I got a spider earring here, you know? Okay, spiders. Now I'm going to teach you what a spider is. Huh? So till now I was just talking about wires and boxes. Now we want to understand what a wire is in order to be able to understand what a spider is. So a wire is a thing with two endpoints, right? Yeah? Think of like an extension lead, something like that. It's a thing with two endpoints. That's a wire. What can you do with wires? You can plug two wires together and you get again a wire. If I take two extension leads, then you get an extension lead. If this extension lead turned out to be elastical, it was a very stupid thing to do, to plug two together, because one does the same thing as two would do, right? So that's the theory of wires. I just explained to you the theories of wires. So you learned something new. What is so wire is a thing with two endpoints, and you can plug two wires together. So what is a spider? A spider is a thing with multiple endpoints. They don't have to be 8, unfortunately. So they can be less. You know, there's naughty children around, and then there is all these sort of chemicals which cause mutations, so they can have 20 legs, whatever. Huh? So the number of legs is not just 8. It can be anything. It can be 0. Ugh. That's a bit scary. Okay, so this is a spider. Now, spider has multiple endpoints. Wire has two endpoints. Gluing wires together gives another wire. Gluing spiders together gives another spider. So that's the same. So basically, if you got two spiders, like here, they fuse together. They flop together in one. The only thing you have to take care of is that the number of legs at the input and the output overall stay the same at both sides of the equation. So you see there's like here 4 on top and 3 at the bottom, at both sides. Yeah? Whether there is one wire between the two spiders or 2 wires or 3 that connect them, it doesn't matter. As long as they're connected, they're going to fuse together. Remember, because there's things to be won if you remember this. Right? So these are spiders. You see, they're both colored green. They're both the same color. Now to the quantum, you see, there's 2 buttons here, green and red. You see that? And that's because the people who designed this, they had some sort of vision about this stuff. So the green and red button. Okay, so now, we go to 2 colors, green and red. So what happens when two spiders meet each other, like when they're the same color, they love each other and they just fuse into one blob. When they are different colors, they hate each other and they give each other like an uppercut. Bang, you see? But spider legs are very fragile, so they fall off when you do that. So important if there are, but so you can only hit with one arm, so it has to be exactly 2 wires between the red and the green for them to go away. So here is the rule. You got 2 spiders, the red and the green one, 2 wires between them, the wires go away. Yeah? Let me remind the rules. Same color, they fuse together, different colors, 2 wires go away. Yeah? Everybody remembers this? Yeah? Okay, cool. What was that? Okay, quantum programs. So we're now gonna look at how a quantum program in a quantum computer looks like. So quantum computers exist, I think. Do you know that? They exist. We do stuff with them. Like Anna does a lot of stuff with them. Yeah? I'm going to mention something at the end of the talk about your stuff. Okay, quantum programs. So this is a quantum program look like in spider language. This is how it looks like in spider language. I mean, you can find this thing in standard quantum computing textbooks. But so the 3 wires you see here, these 3 yellow wires, means 3 qubits. 3 like bits in a classical computer, but this would be 3 quantum bits. 3, and you have to think about time going up. So you have 3, and then there are these 3 things. These are gates. These are like logic gates in a classical computer. So, but like the first one takes the first and the second qubit and does something to them. Then the second gate takes the second and third qubit and does something to them. And the third gate takes again the first and the second and does something to them. So there's a bunch of stuff you do. So it's a quantum program. It's a quantum program. Make sense? Yeah, everybody's with me? No? Don't hesitate to ask questions. Oh yeah, I didn't say that. Okay. It's a red one. Where is the green one?
Hello, they can hear me. To get to that point, did they lose 2 each?
Oh no, nothing got lost yet.
Okay.
Nothing got lost yet. Same picture. But you take a good start.
Yeah.
Nothing. No. This is what I'm saying. This is the program, and we want to simplify it. We want to see if we can simplify it. So this is the program. It's 3 qubits and 3 operations. So 3 qubits, 3 operations. Yeah. And now we want to simplify it. That's what we're going to do now. Okay, what's the first thing we do? I think, yeah, that's you. Yeah, winner. Yeah, so you see there, it's the green, and there's 3 greens which are connected, right? 2 reds which are connected. You remember the rule? Let me go back. Whoop, there. They fuse together. Let's go here. Huh? Boom. Ah, now it's smaller. What now? Was it you? Yeah, okay. So yeah, so there's 2 wires between the red and the green, so they go away. Now, what's next? What? No, 2. I said 2 wires. There have to be 2 wires in between. So this is a little bit more conceptual. Yeah? But no, they're not close enough. They're not connected.
There's no wires on the right. On the left.
No, I mean, so what did I tell you about wires and spiders? Huh? Yes. So that one on the left only has 1 input and output, so it's actually a wire. That was you, huh? Yeah. I mean, I didn't give that rule, but I did tell you that a spider with just 2 is just a wire. So okay. So okay, good. Applause again. Okay. So this was a simple exercise. So we took a quantum program and we simplified it a lot, because from 3 we went to 1. So we simplified it by using our rules. So what I just showed you, taking such a quantum program, not a simple one like this, but a much more complicated one, and then reducing it using the spider stuff, is now the state of the art, which people use in quantum computing companies to reduce quantum circuits. This is the state of the art, this technique, using the spiders. So here, he's a specialist in that. Are you a specialist in that? Kind of, huh? So he does that for his job, like simplifying things with spiders for quantum computers. Okay, now we go to something much more interesting, I even think, conceptually. So, right, quantum versus ordinary wires. So, when you deal with quantum systems and quantum computers, of course, you've got quantum qubits, but then you take a measurement, and then what you read is just classical data. It's just usual data like we deal with all the time. And it's not, it's like what you stick in your normal computer, you know, your movies, your whatever, just ordinary data. And now it would be nice if you can have the two things together in one picture, because if I take a measurement of a quantum system, what I get out is data, which we understand, which you can stick on a normal computer. So we need to get them in one picture. And as it turns out, it can't be simpler. So in von Neumann's language, this is quite a complicated process to represent classical and quantum. It's quite, I mean, I'm not going to say what it is. It's something like you have self-adjoint operators, and then you have to do spectral decomposition and blah, 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 and lots of heavy mathematics. So in spider language, it's quite easy. Quantum is 2 wires, classical is 1 wire. That's pretty easy. And a measurement is a spider. What else? There is nothing else. There's nothing else in the world, there's spiders. The world is entirely made up of spiders. Yeah, so there's nothing else. So we go from quantum 2 wires to classical 1 wire. The other way around, suppose I got a classical bit, like a 0 or a 1, and I want to encode this in a qubit, which is like people who know the language, that's cat 0 or cat 1, that's how they call that. That's how you do this. You go from 1 wire to 2 wires. So that's the opposite. And now yeah? Wait. Otherwise people can't hear this at home. Otherwise people can't hear this at home. It's important.
Yeah. So, those 2 wires, do they represent a superposition? And is that like collapse or no?
No, you have to think of it one system.
Okay.
It's just one system, but you write 2 wires. It's just one system. Of course, so when you say superposition, inside these 2 wires, there can be superpositions, of course, because it's quantum. So all that stuff lives there. Now, for anybody here who knows a little bit of quantum formalism and knows about density matrices, the 2 correspond actually when you write down a density matrix, you write everything double. And that's really what it corresponds to, in case you know about that. If you don't know, don't care. Just think about the quantum world is bigger than the classical, so it needs 2 wires instead of 1. That's really it. That's the intuition. There's more stuff you can stick in there, so you use 2 wires instead of 1. Yeah? But you know, these 2 wires, they can actually carry relationships between them. So there's a lot of things that can be, you have to think of a little wave going between them, you know? A little wave that connects them going between them. You don't have to write it down, but it does capture all these possibilities. Sorry? Yeah.
Is 1 wire 1 bit?
1 wire is like, it's actually probability distributions over a bit. Probability distributions can live in there. And the 2 wires is probability distributions over quantum states. So it's quite rich, all the stuff that can live there. So yeah, but intuitively, just think of classical as a bit and quantum as a qubit. But there's probability distributions can perfectly live on top of that, no problem. Okay, what's the answer? Who was the first one? Yeah, that's just a wire because they're fused together and then you got just a green dot on a wire so it goes away, right? Okay? Prize given? Yeah? Okay. We got another one coming. Whoop! No connection. Who said no connection? Yeah. No connection. Which, okay, let me explain what these two actually mean. So what we do here is we got a classical bit, like 0 or 1. We encode this as a quantum system, and then we measure it. And what comes out is exactly what you stick in. That's what it means. If you start with 0, you encode it as a quantum bit, and then you measure it, it comes out. Now, we have two colors of spiders, which actually means that there are two kinds of measurements. They're different measurements. Like one, for example, if you think about like lights, you could think about two kind of polarizations of light, that you measure one polarization or the other light polarization. If you know a little bit about quantum, you know there is something like position and momentum. And then you've got uncertainty relations, which say that if you know the position, you can't know the momentum, and vice versa. Let's say position, you can't know the speed, and if you know the speed, you can't know where it is. It's a little bit like this. It's like measuring the speed and measuring the position. And so this is something like that, where you encode, say, as position, and then you measure speed. So you measure something else than what you encode in, and then the result is that there is no connection in what comes in and what goes out. No wire means they're unrelated. So what you basically get out is randomness. Because encoding in one mode means, let me come up with another metaphor. Well, I'll do that later. You understand this better. So encoding one mode, and then you measure in the other mode, and they're completely unrelated. So you lose all your information that you encoded. There's nothing left of what you encoded. So that's, of course, quite different from what you perceive in the classical world. You're destroying your data, basically, by doing a measurement in a different way. Okay. Right. Yeah, I think you're right. I couldn't hear it, but you're right. So basically, all the doubles go away. So so all the double wires go away again. Let me spend some time on explaining this picture, because then you may not know exactly what's going on here. It needs a little bit more. So you see two wires coming in, a green dot, and then two wires coming out. Basically what that means is I've got a quantum system, then it goes into this measurement, and I got a quantum system out, which means the system is still there. It's still there. We didn't destroy it. The single wire which comes out is your measurement result. So I got a quantum system going on, I do a green measurement, I get some outcome, and the quantum system is still there. Then I do a red measurement, quantum system is still there, but I got a new outcome. Then I do a green measurement, quantum system is still there. Yeah, so, yeah? Oh, this is all one. All one, just one.
With 3 outputs?
No, those are your bits. So you know, I got a qubit, I do a measurement, I get a bit. I do another measurement, I get a bit. It's still the same qubit. I do another measurement, I get a bit. Good question. Still the same qubit. So I've got a thing, I measure it. Like, okay, I got a car. I say, you look at which color the car has. And then you look at which brand the car is. And then, again, you look at which color it is. That's what we are doing. So we get a car, we first look at the color, then we look at the brand, and then we look at the color again. And so we get twice information about the color, one time information about the brand. Now what this picture shows is that the first time you look at a color and the second time you look at a color, they have nothing to do with each other, whatever you observe. They're completely unrelated. First time you looked at a color and the second time you look at a color, the results are completely unrelated, because in the middle you looked at the brand. So that's what this picture is showing.
I have a question.
Yep.
Is that that?
On the right, why don't we remove the red one? Because it's just a wire.
Oh, no, it's only one wire, not two wires. It's only one endpoint.
Oh, okay.
If it would be two endpoints, then yeah, you could, but now it's only one, so it's even less.
So can you explain what's happening at the top? Is it one normal bit and one quantum bit coming out? At the very
It's one quantum bit and 3 classical. So 3 bits and 1 quantum bit. The single wires are bits. The double wire is a quantum bit.
Right. Okay, thank you.
Yeah. So we have one system, and we then do 3 times a measurement of the same thing, like with my car. So if I got the notebook, I look at the color of my car, I said, this color. Then I look at the brand, then I write down the brand, and then I look again at the color, then I write down the color. So I got 3 things. I've taken note of. So now, why is this happening? You remember von Neumann, and you remember the little girl in the room with the balloon, that when she's going to try to find where the balloon is, she's going to kick the balloon, and the balloon's going to be somewhere else. Same happens here. Yes?
So as you said, quantum state is still there whether you are doing some measurement on that green spider over there. But what I realized is, if you measure quantum state, why didn't it collapse into classical
Well, that's what
state?
I'm about to say.
Oh, okay.
That's exactly what I'm about to say. So you remember the girl in the room with the balloon? Like, she finds the balloon, she kicks the balloon is somewhere else than actually where she found it. This is von Neumann's collapse postulate. So when you do the first measurement, just by asking the question, you disturb the state. It will change. Therefore, you got a different state. And then the red one will change it even more. It will completely collapse in a different direction, which is completely unrelated to the second observation. So it's because of this change of state that this happens, that the first one is completely unrelated to the third one. So that's the end. That's why this is happening. But you don't have to write down that you collapse. It's just implicit. It's all inside the language, inside. You don't have to do it by hand anymore. But this is the manifestation of what you were asking. Make sense? Yeah. Okay. Right. So I'm gonna head. So yeah, like I said, my fonts they were so beautiful, like chalkboard fonts. But okay.
We actually have a question up here.
Okay. Yeah.
Yeah, there was just me over here. If we go back to the last slide with the diagram, the one thing that I'm not fully wrapping my head around is there any difference in terms of the directionality? Like, because the first green spider has the quantum bit notation, whatever you want to call it, come from the top.
So very good question. Very good question. So basically what you see on the left, I mean, I was a little bit like hand-wavy about it. What you see is like an operational description of what you're doing. You got a qubit, you measure. Qubit's still there. You measure again, qubit's still there. You measure again. What you see on the right-hand side is like a mathematical calculation. So the qubits are, of course, still there, but it tells you that whatever comes out of the first single wire is totally unrelated to whatever comes out of the third single wire. It's a calculation. I mean, this is true here too. Let me go back. This is true here too. Wait, here. Of course, on the left-hand side, you got a classical thing, then a qubit, and then a classical thing. On the right-hand side, the qubit, but that's a mathematical representation of the relationships between the two. Make sense? So what you do is on the left. I could have made this more explicit with saying, and I say, it's like when you do a calculation, you add some things up, like, the right side is like the physics, the left side is the physics, the right side is actually the math, so to say. Good observation, good observation. You deserve a book. Okay, here, book. So from now on, smart questions get books from you. Yeah, because we're in question time. Okay, so the language which I gave you till now is not enough to capture all of quantum mechanics. You can't capture all of quantum mechanics just with green and red spiders, which you can imagine. It's just 2 objects. So what you need to do is, I've got it written down here, you need to decorate your spiders. So initially we were going to decorate them with phases of the moon. Physicists call these phases. So actually you stick on each spider, you can stick a phase. Initially we were going to do this with phases of the moon, and then Stefano was actually drawing most of the pictures. After having drawn like 50 phases of the moon, he gave up. We're going to do numbers instead. We're not going to do phases of the moon. Like the obsession was, I said, I don't want to see a single number in this book. But okay, so we gave up and we actually did include numbers. So what happened, like these spiders can now carry decorations like spiders do. They typically carry decorations. And then these decorations will simply add up. So if it's decorated with 90, then they will simply add up. Yeah? And so you see 290s become 180. So that's like a bit an extension of our spider fusion rule, but otherwise it is the same. So you can decorate your spiders and your decorations add up. And then another rule, which we're not going to use explicitly, is a rule which we call square popping. if you got a square of spiders like that on the left-hand side, you can replace it with the one on the right-hand side. I'm not going to give examples here because that would take us too far. But the reason I give you these two rules, we kind of implicitly will using it later. This rule and this rule is because of the following result. I'm not saying here that John von Neumann is nothing but a book. That's not what I'm saying. So what I'm saying here, and this was proven, a very, very difficult thing, which was proven by that guy. Put your hand in the air. It was proven by him, Harney. He showed that any equation you can derive in von Neumann's original quantum language, so anything which people consider true in quantum mechanics, you can derive with the pictures. Everything. Stand up. Stand up. I mean, this is something we had conjectured for a very long time, sort of, vaguely. But, I mean, to be honest, I actually didn't think it was going to be true. Did you think it was going to be true? I would have put money against it. Anyway, it turned out to be true. Turned out to be true. So that's a really big deal. And this basically means that for any practical thing, you can just use the pictures now, which is what is really happening in quantum technology. Lots of people are now using these pictures for many different things, very practical things like error correction. I already gave the example of simplifying quantum programs, very engineering stuff like correcting errors in your quantum programs, in quantum computations, all this sort of stuff. People are now using the spiders. You're working on that, Leah, right? Error correction. Yeah, you're doing that. Okay, so this is a very important result. So basically, if we go back all the time, like von Neumann wanted alternative quantum formalism, this is generally an alternative quantum formalism. This is a genuine alternative to the quantum formalism, which you can teach to kids, and which people now in quantum computing and IBM, Google, everywhere, they're using all of this now. They're all starting to use this. I mean, this is just a slide, an example of some paper. I don't know which paper this is. Do you know? It's about topological encoding of blah, blah, blah or something. I don't know. It's topological. It's rewriting topological things in blah, blah, blah. But you see this arrow. You say, okay, we got this, then we go through our green and red spiders, and then we got this. This is what you see now everywhere in quantum technology papers. Well, yeah. I mean, you just use it to do your calculation. You just use it to do your calculation because it's so much more. It's not just that it's more intuitive. It's also, for example, much easier to stick it in a computer and let a computer do this because this is a discrete system. So it has lots and lots of advantages. Lots and lots of advantages. And like the kids say, it's fun. Okay. I mean, now I'm going to take you to the end of the book. Let's see if we get through that. But let's just take it. I mean, it's not essential that I do that, but because this is literally the end of the book. So I want to take you all the way there. Any questions at this point? Yeah? Oh, 2 questions.
Is it still to me? On the last slide, can we go back one? Why with the spider diagram, there's green on the left and red on the right, and then they swap places?
Well, this is exactly this.
So why is that?
Oh, it's just true.
Okay.
It's a law. It's a law. It's like a law. It's something you can use. But the thing is, when you have some picture with red and green spiders and you got a square, you can always get rid of it. And this is something if you can, for example, go to the usual language of quantum, translate this, and then you prove that this is true. But the magic is you don't need anything more. That's what I was saying. Only the spider fusion thing and this rule, and you get everything. Which is remarkable that you don't need anything more. So that's the magic of this, that you don't need anything more. And so that picture there is actually the same picture as the one I showed, with a little twist. Mathematicians, if there are mathematicians here, this is what people call a bialgebra. It has a name in maths. It's called a bialgebra.
Can I follow that up? The same place over here. Yep, hello.
Yeah, okay, yeah. Yeah,
So
the spots are...
The example before, you could yeah, you could say that they don't switch because you just drop the bottom two and then you cross the
No,
lines.
no. So if you look at the connections, you see that what on the left-hand side is connected to red is on the right-hand side connected to green. What on the left-hand side is connected to green is on the right-hand side is connected to red. And then there happens to be a little wire between them. So the colors at all, but this is very useful because it may be the case that there is stuff that you can't fuse, and then you use this, and then you can fuse because the colors are swapped. So it's a very useful thing to have in your calculations if you think, and that's why it's so powerful. That's why this simple rule is so powerful, because it's like when something is blocked like your toilet, it unblocks. You know, it unblocks. Everything can come through. It's like what is it, Mr. What's it? Mr. Muscle. This is Mr. Muscle of graphical reasoning.
Well, yeah, just a question. I know this is a physics-oriented lecture, but are the chemists simplifying quantum chemistry using these types of
He's
techniques?
working on that. We have a lot of chemists in our company, and he's working with them. So these things can be differentiated and integrated. So you can write down Hamiltonians of chemical systems and all of that. So we got about, if you say ZX, so the technical term for this thing is ZX calculus, and you can find papers with ZX calculus and Hamiltonians and representation of chemicals. This is all very new. This is all very, very new, but this is happening. Yes, this is happening. Wait, all these smart questions get a book, eh? So there was another one up there. So I need to get rid of these. So when you ask a smart question, just call out.
Hey.
Yeah. Yeah.
Over here you have showed lattice braiding and circuit reduction, but...
So wait, this is not a braid.
No?
This is the same.
Okay, and...
sorry, it's just a notation, but it's not really a braid.
Okay, and over here you have showed all these circuits, but how would one come up with these circuits before, like, you show the reduction part? Like, what's the...
Oh, you directly
essence?
Translate your quantum circuits into this. So basically,
yeah,
if you know, now I'm going to say something technical now, which some people may not understand, but like, these are all C0 gates. These are C0 gates, and then your spiders with decorations, they're phase gates. So and then there is also a gate which actually, if you push it through a spider, changes the color, and that would be the Halmar. So you translate directly.
Yeah, the question is, how would you come up with these quantum circuits in the first place?
Oh, I mean, you got a task like a problem that you want to solve, and then you need to come up with a program that does it. It's the same as in classical programming. You need to come up with a program that solves your task. That's an art. That's a different kind of art, of course. Coming up with something that solves a problem, and that's quantum algorithm development. You got a problem, and you want to hope that maybe quantum mechanically you can do this better than classically, and then it's very hard to come up with it. But that's the whole science of it, to come up with that. So that's a very hard task. Okay, that's a smart question again. I mean, there were more smart questions which didn't get books, but you have to just like scream. You had a question? Wait, we have to wait for one of the microphones. Oh, one more questions. Okay.
What is the, for the horizontal connections, what's the flow of logic?
Very good question. Very good question. I mean, basically the way to think about it intuitively is that, and I'm going to use the word, is that you entangle these two things. You grab them together and you put them in a certain connection. Now, as it turns out, formally, doing this or that is exactly the same. But intuitively, I think it's better if you denote it like that, because really what Schrödinger was talking about, you put them in some sort of twin state. You're sticking them in a twin state. And then they are connected. Whatever comes out after it, they are very much connected. And that's where the quantum magic can happen. Formally, this and this is the same. Turns out, this is something you can prove.
Thank you.
Next question's over here in the blue.
You already had one.
So I'm not sure whether this question is the same as the last one, but in all your diagrams before, you've been flowing from bottom to top.
It's the same question.
Yeah.
Like the reason we write like this is because if we would write it like two things coming out in green and then one coming out in red, or two things coming out in red and then two coming in green, it's the same thing. And then therefore we denote it like that. But yeah, good question. That's a book. I mean, we prove all that. In the book, we prove all that stuff, of course. But I mean, I didn't have time here. Yeah.
Hi, with the square popping, I noticed that the two wires at the top, back to it.
Let me go back. Yeah?
Yeah, the two wires coming out were crossing over. Is that significant?
No, that's a good question again. Like in many branches of mathematics and stuff like that, this is not equal to that.
Yeah.
But here it's the same, actually. It's like electricity wires. If you put the knot, it doesn't matter.
Okay.
But there's lots of fields where this actually does matter.
Okay, but could they have just been coming out like that and not crossing?
Well, I mean, that's a very good question because we're writing this stuff on a piece of paper. And on a piece of paper, okay, now I'm going to say something very complicated, and this is something you can dream about all night. Because it's like we write on a piece of paper. A piece of paper is two-dimensional. So there's just no way you can do what you said that it does. You can't do this in 4 dimensions. In 4 dimensions, everything moves through everything. And there are no knots in 4 dimensions. That doesn't exist. There's no concept of a knot in 4 dimensions. And then, yeah, that vanishes. But you have to go to 4 dimensions.
I'll get some 4-dimensional paper.
Yeah. So that was a good question.
Yeah. So can the red and green spiders only do one thing, or could you like define the red spider and the green spider to do different things?
Of course, I mean, so these rules which we have exactly correspond to what you get in quantum mechanics. Of course, you can come up with So, for example, this was all for qubits in 2 dimensions. When you go to higher dimensions, 3 dimensions, 4 dimensions, 5 dimensions, you can also define, like you could have you could change from a bit which has 2 values to something that has 3 values, 4 values, whatever. If you go higher, then your rules already become more involved. And there are completely different calculi we have with completely different kind of spiders which serve their purpose. Like Alex's PhD was about exploding spiders. So they had completely different rules. When they met each other, they just exploded in nothing. And this was very useful. And people are still using that. Now they actually moved all of them together in some 3 kinds of spiders, some exploding ones. And so yeah, there is a whole business of developing new of these calculi which are useful. They have to be useful for something. In computer science, just classical programming, a lot of these things have come in now too. They start to use that too, and very useful things are being done there too. And then sometimes they have to, for example, they don't have these decorations because they make no sense in traditional computer science, for example. So yeah, there's lots of variations possible. That's a good question.
We have 2 questions down here, and then
yeah, that's a prize, huh?
Yeah,
oh, okay.
Where do the decorated spiders come into play with this? Are all spiders decorated?
So the real reason is, so what you want to do is, suppose you got any quantum system. You want to write it down in the language of spiders. That's what you want to do. And if you wouldn't have your decorations, your language isn't rich enough to represent all possible quantum states. So so this is a result which I didn't write down, but there is every quantum state, if you know about linear algebra, every matrix can be written down in terms of spiders if you got decorations.
So are they all decorated? Are they
Well, I mean,
decorated?
the non-decorated is like having a 0. Non-decorated simply means there's a 0.
Okay.
Basic example of what a red spider represents and what a green spider represents physically.
Good question. So did everybody hear that question? Was it through the microphone? Because that's otherwise I have to repeat it. Let me repeat it. So the question was, can you give some idea of what a green and a red spider correspond to physically? I already gave you the intuition that they correspond to different measurements, different observables. Like one would be position, the other one would be momentum. Okay, I've got a board. So this is quite technical, but so if this is a spider, and I take one with 2 legs in and 2 legs out, this is a bit complicated, what I'm going to say. Then this would correspond to copying the basis vectors, copying the eigenstates. And if you've got 2 different observables, this would copy different things. So that's really the physical basis of it. And then because of the no cloning theorem, you know that the only things you can copy are actually the basis vectors and eigenstates. So that's really the easiest physics. But one of the things is most of these spiders, they're not sort of things you can easily do. The magic of it is when you put them together, you get stuff that's really physical, like in the circuits. It's the whole idea is you break something complex down in simple bits, which you can very easily reason about. That's the idea here. That's the main idea.
Thank you. Thanks for your questions, everyone. I just want to make sure Bob has a few minutes to finish the end of his talk,
Well,
and then
I mean,
we'll go back to a Q&A at the end.
Yeah, so okay, so okay, so I was going to explain non-locality, but I'm not going to do that because it's going to take too much time. I'm sorry, but you can read it in the book. So I'll just give the idea. I'll give the idea of what we would be proven. But you can read it in there. Huh? So the idea is, for example, if you got a twin, then you know that they have a common origin, which is their common genetic material, which at some point was together and then split. They get the same genetic material, and that's why they are the same. So there is some common origin of why the twins are exactly the same. Now, quantum non-locality means that you got connections between things, but you can't explain them in that way anymore. There is no way you can explain this by some common origin. So I was going to prove this using the spider diagrams, that you can't get that. But you can read this in the book, like, whatever. Look, just enjoy my beautiful slides. Ooh, look, spiders, more spiders. Ooh. So it's quite a complex argument. It's the end of the book. But I just want to, okay, let's go through the argument, blah, blah. It doesn't matter, you do some calculations, blah, 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 blah. And then this is the picture that says you got a common origin. That's the twin picture. You do blah, 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 blah. And then at the end, you say 0 is not equal to 1. And 0 not being equal to 1 means that quantum world can't be explained by some common origin. So it's all in there. The kids understand it. Let me remind you. They spend 1 to 2 hours a week. So you can't complain about anything. We've handed out a lot of books, so you can learn it yourself. So I'm going to use the last few minutes to say a few extra things. So all resources, lectures and exercise will soon be made available on a dedicated Quantinuum website. We have been trying to do this for a long time, and we're all very busy. But Pete, where's Pete? Can't see him. It's going to happen, huh? We're going to make everything available. Like we probably are going to do something that you have to register so that we get some idea of which people actually are accessing, and that we have some idea from where in the world people are accessing and stuff like that. It's all useful information to have. My main day job today, just to end, is basically quantum AI. And so for example, I already referred to Anna there. So something we are doing now, using these pictures and all of that sort of stuff, is trying to come up with a new version of AI which is interpretable, which you understand what's going on, which is not the black boxes where you don't know what's going to go on, like where everybody's complaining about now. So that's mainly what I'm doing during the day now, because these pictures, that's when I was a little kid when I did all of that and came up with that. I mean, the spiders go back to 2007, so it's quite a while already. It took quite a while to convince people that this was actually good for anything, and now everybody's using it. So that's the sort of stuff we've been doing, and we do this with real quantum computers. We do like AI with quantum computers already. So we teach them stuff, the quantum computers, then we ask questions, and then the thing is, thanks to the pictures, we actually understand what's going on, unlike what people are doing in usual machine learning, large language models, where we don't know what's going on. So that's my day job. And you see my T-shirt here. This is compositional intelligence. Am I the only one with this shirt? Okay. Composition, and it stands for intelligence, like in artificial intelligence. Compositional, you remember Schrödinger, plugging stuff together. It's the plugging stuff together structure which we make explicit that allows us to understand what's actually going on in AI. So that's mainly what my team at Continuum in Oxford is doing. I got an eye job too. We play quantum music. And when was it? I mean, you were involved in that, Anna. Like 2021, we basically started generating music with a quantum computer. We were the first one to do that. And then the song we made, Bob Cigar Bus, ended up #1 in some classical charts. But don't go and listen because it's bad. But so is there anybody from Mott here? Nobody? Because they were going to come with 5 people. Who's there? Again, I can't see. Okay, there, you're all Mott. Okay, good. So there is now this company called Mott, which actually builds quantum musical instruments. And this is not a joke. It's not a joke in the sense like these things exist. And like, for example, so this is Mott, that's their logo, although I think they just got a new website. For example, this summer I played on very big festivals, like in Wacken, which is the biggest metal festival in the world, and in Holland, what was the name again? Lowlands. And I was using on stage quantum instruments. So this is a real thing. And so this company is based in London here. It's quite new. You can look them up on their website, what they're doing. And so, yeah, I thought it was a good thing to end with, like quantum music. Anybody has a good question? Because there's still some books to be
Should we
given away.
Let's give Bob a big round of applause.